All right, so while this is buffering here, I'm going to get the computer screen ready to rock. Where am I? Which? Oh, yeah. And then this is probably the last time we'll be doing this plotting in class, but I'll try and explain why we're doing this in just a second. Make sure this is getting fired up. So everybody's got a laptop or something? You got something, you're good, you're good, you're good. Okay, everybody's got their, so if you've got Excel, that's what we're going to be working with. I'll try this a little bit differently than I did this morning. Error occurred. Hey, Jacob, can you confirm the live stream's working? Because I know you're going to try and watch it later. I'm going to try and get my screen share going.
Yeah, it's going.
Okay. I don't know why it does that to me. You see, this is what it shows me on my screen, but it seems like it's working. It's probably just buffering or something.
It's playing for me. It'll probably work if you refresh that.
Okay. All right. That's fine. Watch, I'll probably start talking and it'll auto refresh and then it'll interrupt me like 30 minutes from now. I'll be like, whoa, jump out of my chair. All right. And so let me get this so you can see here. All right. So last time, if you recall, we made some plots that looked like this. We talked about time on this axis, and I think we had voltage or current. And do you recall we saw some stuff that looked like some kind of sine wave, and then one of them was usually out of phase, where so there might have been some angle between them. Do you remember that kind of? Sorry, that's a terrible looking picture. So that's what we did last time. Well, now I want to talk about one particular thing, and I'm going to try and discuss it here while this is on the screen. Do you recall that this was called the current amplitude, the largest amount of current there? And I believe we called that I max. The idea, that's the current amplitude there. Sorry, it's poorly labeled. So, and if you recall a few weeks ago, or last week, the current amplitude depends on the frequency used. Remember that? So sometimes there would be almost no current amplitude. Sometimes there would be large current amplitude. So tonight, what we're going to start with is we want to do a new plot. We want to understand as the frequency changes, or the angular frequency, we want to see what happens to I max. So again, this is not current. This is current amplitude, right? And so the idea is, this is that one plot, if you recall, that kind of looked like this weird shape where there was kind of a peak and then it went back down like that. And the idea is, as you got to really high frequency, there wasn't much current amplitude. When you got to really low frequencies, there wasn't much current amplitude. And right at the resonance frequency, there was a lot of current amplitude. That's our goal to understand tonight, for starters. Everybody okay with that? Okay, I'm going to clear these drawings and let's get to work. All right, so let's start with something simple. Let's say we have a resistor in ohms. I'm not going to worry too much about italics, but I am going to get these symbols right. So I'm going to type SYM for symbol font. And at any time, if you need to stop me, let's just say it's a small resistance. So let's say 0.7. Oh, and I'm going to center everything just because that's how I like to do it. So I like everything to be centered. All right. Let's say we have an inductance. Does anybody remember the units for inductance? Henries. And so let's just say 3. And then for our capacitance in farads, let's say 0.03883 for no good reason. All right. I think these are the numbers I used this morning, and I think they worked pretty well. And I don't remember. Okay. So, all right. So these are going to be the main parameters. Now we usually have a source voltage amplitude, right? Whoops. That's going to be in volts. Let's say 3.5, just because, again, I'm just picking some numbers that I think I used this morning. Okay, remember that V0 is not the voltage of the source. It's the voltage amplitude of the source. Everybody good with that? I know I say this crap a lot, but okay, so let me ask you this. If we know this stuff, maybe we need to have an operating frequency. Well, in this case, our goal here is we want to tabulate how this thing performs at a variety of different operating frequencies. So again, I'm using the symbol font. W in the symbol font gave me omega. So lowercase w gives me lowercase omega, uppercase omega gave me this one. And now I don't want to start at 0. Normally we start with 0 as the frequency, but we're going to run into trouble if we try and compute XL and XC. Which one of these is going to give me trouble at 0 frequency? XC. Does anybody remember the equation for XC? Yeah, XC goes to infinity if we plug in 0 for omega. So I'll write these up here. What was XL? Does anybody remember? Somebody else maybe? Yeah, and what page are you on, just in case somebody needs that? Okay, it's on the equation sheet on the back. Very good. Then how about this? What was the equation for impedance? What was the letter for impedance? Oh, that's inductance. Impedance was what? Z. What's the equation for Z?
Square root of R squared plus.
Got it.
XL minus XC squared.
Yep, that's it. So I'm just putting this stuff here so we kind of can, you guys can see that on the screen, is that right? Is that legible to those of you in the classroom with me?
Yeah.
How about those of you on Zoom? Uh-oh, I just screwed up. It's minus, isn't it? Can you see on Zoom okay?
Yeah, it looks fine.
Okay, and so XC, and then that whole thing has to be squared, right? There was one other piece, a couple other pieces here, right? Let's say I want to get the phase angle. Does anybody remember the phase angle equation? Inverse tan of,
XL minus XC over R.
that's right. So I'm just getting all this stuff here so that we have it. It's the, is there an easy way to remember these equations so that we don't have to just blindly memorize them? Maybe a picture that might help? The phase triangle. Do you remember that? So even though this isn't on your equation sheet, I highly recommend you remember this stuff because then you don't have to try and remember so much. This side is R, this side is Z, and this side is XL minus XC. That's how I remember it. I'm like, oh, wait, was it what over what? This helps me, and notice we could get cosine phi, which is the power factor. If you read the equation sheet, that's on there somewhere. All right. Finally, one last piece of information that we might need. How do I get the current amplitude? Current amplitude was I max. Does anybody remember that? V naught over Z. It's a lot like Ohm's law, except now we have to use Z, right? V naught over Z. So my claim is we should actually be able to use these equations on the right side over here to figure out all of these things over here. So I'm going to get this in ohms. I want to get this one in ohms. Again, technically I should be formatting correctly, but we got to get through this crap, right? Okay, and then we could probably figure out Z in ohms, agreed? What else could I figure out? Phase angle. When I figure it out, it's probably going to spit it out in radians. If you care, you could get the phase angle, that's F in the symbol font, SYM. Well, I may want to get that in degrees because that's what makes sense to most people. We don't think in radians at first. And then the last thing I could get, shouldn't I be able to get I max in amps? All right. So our goal is to convert this information into this information and be able to plot it. Everybody understand? If you want to race ahead, go for it. But I want to go again. This is probably the first part that you might want to watch. 0.1 is a good starting frequency for this set of numbers. Now, instead of just typing 0.2 and filling down, I'm going to say this equals the cell above me plus 0.1. So I'm going to go in 0.1 increments. If I wasn't sure if that was a good size, how could I tell that's a good size? How could I tell that 0.1 is a good step size? Any ideas? I know this may seem stupid to ask this question, but this is kind of useful in a large range of things. Do you remember how we figured out step size last time?
Wasn't it with the DT?
Yeah, the DT. How did we figure out DT last time? Do you remember? The period. Well, now I'm going by omegas. Do we know any special values of omega that might be useful as a reference to kind of get a feeling for this problem? What's the one special frequency called? Yeah. Isn't there a formula for that? What was the formula for omega naught?
1 over square root LC.
Yeah, let's go ahead and get that in here. So this is equal to 1 divided by square root of LC. Does that make sense? So if I wasn't sure what frequencies to use, I could punch these numbers in, and this gives me a pretty good idea that, oh, okay, if I go by tenths of a radian, this is going to be a really small step size compared to that. Agreed? All right. So that's how I did this. I was basically saying, look, I want this to be really small. My increment size is 10 times smaller than my resonance frequency. That should be pretty smooth. Okay. Now you could say, why don't you just fill this now, dude? Why don't you just fill it all down? Well, if I just am patient, I can fill in all of these and then fill them all down at once and only have to fill down once. So now, these two here, oops, let's make this a pink color so it kind of matches. Okay. If I use those pink formulas over there, what do I get? For X sub L, what do I need to type?
One over XL. It is E2 times B2.
No. Why is it not E2?
Oh shoot, no, not omega naught. It's
Yeah.
A5.
Yeah.
A5
And so,
times
good. I'm trying to do this all the time. We want to do A5 times what?
times B2.
Right. And then if I type B2, do you agree I need to slap some dollar signs on there? Because the inductance is a constant. The angular frequency is what's changing here. We're sweeping omega. All right. So there's that one. All right. Somebody else. How am I going to get X sub C? 1 over, yeah, what is it?
Over A5 times C.
Yep. And now for me, you can do this lots of ways. I'm going to divide by A5, and then I'm going to divide by this one and put on the dollar signs. The reason is then I have fewer parens to think about. You can do it 1 divided by parentheses of blah, blah, blah if you want. We got our constant there. Whoa. Look at these numbers. Compare XL and XC. Does that make sense? Is this a high frequency or a low frequency? We're at 0.1. Compare that to omega naught. Is this a high frequency or a low frequency? Low, right? It's low compared to resonance. So which term should dominate? Capacitor, it is. Okay. Now Z, let's do this column here. I'm going to make this one in purple, all right? Just so it kind of matches. It's kind of a nice purpley color. It doesn't pop that much. Let's use pure purple here, darker purple. Whatever, it's purplish. Okay, so now Z, you agree we've got it? Punch it in. Square root of R squared, does that need to be a constant or not? Does the resistance need to be a constant?
Yes.
Yes.
So I F4 it or put the dollar signs in and square it. Plus XL. What is XL? B5? Does that need to be a constant? Yes or no? Is XL going to change when I go to a different value of omega? Yes, so let's keep it in there, all right? And then what was XC? C5?
Yeah.
Do you agree that one also should be changing? And so I've just put a couple of spaces in there to make it easier to read. Is everybody okay with that? Okay, notice the capacitance is almost all of it. Anybody know the function for inverse tangent? Take a guess.
A10.
A tan it is. Right? Okay, and so now we need to do XL minus XC. So I'm going to put some parentheses around that and then divide by the resistance. Get this. So XL minus XC, what is that? B5 minus C5. And then I'm going to divide by the resistance, which is A2. Is any of that a constant or not? The resistance. So I'm going to put an F4 on that to put the dollar signs on. All right, so that's looking good. Does that phase angle make sense? Well, let's put it in degrees. Does anybody know how to write that in degrees? Equals degrees of this. It's about -90. Do you agree? Let's get a few less sig figs on these. All right, so it's it's a negative angle. Should the phase angle be negative? Capacitance is dominating negative phase angle. That's something we're supposed to remember, and it doesn't really stick until you do it a bunch of times. So I was hoping you'd say, oh yeah, that does seem pretty reasonable. Now I'm going to make this one green just so it stands out here. Maybe I'll do the same with this one. All right, so our phase angles are in green. And now I max, I chose this orange color for some stupid reason. Let's make that some stupid orange color. All right. Okay, so in this case, what should I type? I want to get this calculated. What should I do? What's the formula? Yeah, do we have V naught?
Yes.
Yeah, what cell is it?
E2.
Dollar sign or not?
Yes.
Okay, and then we're going to divide by D5, dollar sign or not? No, right? Because the Z is good. All right, so now what we could do, I could fill these all down one unit. And now I could grab the second row and fill that down because of the way I wrote this first cell. Now I have a formula in every cell, so I can just fill this down. How far should I go down until I hit what omega, in your opinion? We know the resonance frequency is about 3. Just take a guess with your gut, and I'll tell you if you're right or wrong. Just go with your gut. What sounds like a good number for our largest value of omega? 6 might be good. And I was going to go all the way to 10. From experience, I know the capacitor side tends to change more rapidly because it's a 1/over. So let's go all the way down to 10. 6 would be a great first start. And then you'd be like, huh, maybe I'll check it. So drag it all the way down until it goes to 10. I don't know how far that is. Whoa, that's a little too far. Whatever, it doesn't matter. Data is cheap, all right? We're living the dream of infinite data. All right. Okay, so far so good. Now what we want to do is we want to make these plots. So highlight the omega column down to 10. And then let's get the Z column. Okay, And I'm going to insert this plot. Let's not try, I'm going to do a scatter plot. I'm going to put a title on this. Oops. Z versus omega, because I'm lazy. All right. I'm going to make this a little bit small. We can blow it up in a minute. But one thing I might do is come into here, axis options, and I'm going to make this top out at 10, right? We're going to make all of these stop at 10, right? And this is what I was saying, why do you see why now, if you look at the screen, why we might want to go past 6? Just because it's not as dramatic. We might even want to go all the way out to 50 or something. Turns out for this particular set of numbers, it takes that inductor a while to ramp up because these frequencies are so low. All right, so there's that one. And maybe on this case, maybe on the vertical axis, I'm going to change the scale to, how about we just go up to 30? I think that makes it a little bit more dramatic. You could tell it's still going to infinity as you go to 0, but it's a little easier to see. Okay, is everybody okay with Z versus omega? Okay. I would like to get rid of these equations on the right side. Is that okay? Does anybody still need the equations on the right side, or are you good out here? Okay, I'm clearing just so I have a little bit more room. All right. Okay, let's plot, do me a favor, let's plot I max versus omega for the same region. So let's do this one down to 10. Now I'm going to press and hold control after selecting. And let's get this I data. All right, just a number. Oh, shoot. Screwed up. Start over. 10. There we go. Insert. Plot. Do you recognize that one? That's the one that we were supposedly trying to learn about today. I'm going to change this to 10, just so I can see it a little bit better. I'm going to shrink it down, try and make it the same size as the other one here. I guess we could probably go just up to 5, right? Let's do that. Let's go to 5 by 1. All right. Thank you for your patience here. These are the two big ones. We'll do the phase angle in a minute. All right. They don't quite line up, do they? You see that? It's because the numbers aren't quite the same. There we go. Is that better? That's pretty close. All right. Now, I was telling some people today as I was sitting out there, like, if you want your students to pass tests and labs where they have to do plots, maybe you should do the plots with them. I discovered that we finally have something we can work with here. And I apologize if it took us a while to get there, but this is coming on your next test and the final exam is your ability to understand these plots. In particular, I want to talk about a couple major things. Z is like the total amount of ohms, okay? It's not resistance, it's impedance. But look at these two charts here, right? What do you think is going to happen to these two charts if I change some of the numbers? Because we've coded these up, now we can finally have some fun. Don't do anything yet, let's think. If I increase the resistance, what should happen to these plots? In particular, I can see that right now, right, the resonance, actually, let me move this just a little bit here. Give me just a second. I want to move this over so we can see everything. Okay, this is the part we really want to learn from, all right? So stay sharp. You can see the resonance frequency is at about 3. Do you see that this is the omega naught right here? This is omega naught on our plot. What's going to happen if I change the resistance? In particular, if I change the resistance, should omega not change or will it not change? Does omega naught depend on resistance in the formulas we've been playing with?
No.
No. So if I change the resistance, is that going to shift things left or right on these plots?
No.
No. But if I change the resistance to say 7 and hit enter, what will happen? Let me hit escape. Remember, what is this second plot? Do you remember what I was plotting here? It was I max versus omega. If you increase resistance, generally speaking, what happens to current? It goes down. So if you increase resistance, what do you think should happen to current amplitude?
Should get smaller.
Should get smaller. Watch what happens when I hit 7 here. What about Z? What's going to happen to Z? Z is the total amount of ohms. If you add more resistance ohms, what should happen to Z?
It's going to get larger.
You see that? Try playing around with it now. Right? Depending on what value you use, whoa, you can get these crazy sharp spikes or these smooth ones. And so if you use 1 ohm or 2 ohms, we could see maybe if I change this vertical scale even more, or maybe just make it as big as possible, right? You can kind of see it a little bit better now. But the idea is if you change the ohms, notice this fact. What's this value right here? About approximately 5. At resonance, what does Z equal? The resistance. So the impedance plot goes to a minimum value of resistor R at the resonance frequency omega naught. Did that make any sense? When you're at resonance, think about this. And I'm going to write all these words down on the board to summarize when we're done. Okay, so if you're wondering, is he going to write this down? Yes. When we're done, I'm going to summarize on the whiteboard. But at resonance, XL equals XC. That's a fact. So Z is equal to what value? If XL is equal to XC, what do you get for the formula for Z? The pirate says R. That's what this plot is showing us. Okay. Let me get rid of this, and this. Oops. This. All right, there we go. Now, let's put this back down to say 2.5 or something. Let's say, what was it? 0.7 is what we started with, right? Okay, now what's going to happen if I increase the inductance? What do you think is going to happen to these plots? If you increase the inductance, is that going to change the height on this lower plot down here? Is that going to change the largest peak height? What do you think? What's that?
No.
No. How do we figure out this peak height? Do you remember what equation did we use for I max?
V naught over Z.
V naught over Z. So what is the special value of the max I max? I'm going to say that again. What is the special value of the max I max? Right here. What is this peak height? It's always V naught over Z, right? But what's the special frequency here? Omega naught. What is the special value of Z at omega naught?
R.
So this is I max max is equal to V naught over R. Do you agree? Because the minimum impedance is resistance R. So the maximum max current is V naught over R. Did that make any sense at all? All right, so, okay. So far, so good. Well, tell me again, what's gonna happen if I increase the inductance? Is it gonna change the height? No, what will it change? If I
The
change the, go ahead, go ahead.
like it's gonna shift.
Yeah, which way do
Okay.
you think? So just take a guess. If I increase the L value, which way should it shift it?
Um, to the left because it gets more negative.
Let's see, increasing L should make omega naught smaller, shifting it to the left is right. So let's try 30. Whoa, look at that. Very good, very good. So I'm gonna undo that. What about if I make C bigger? What if I make this 0.4? Is that gonna shift it the other way?
Yes.
What's that?
I said yeah.
Oh, take
I
a
think
look.
so. Oh.
Same way. So remember, if you increase L or C, they both affect the resonance the same. So what they affect differently is these reactances. So the reactances are going to change differently. But remember, increasing L or increasing C, both of those screw with the resonance to the left. Did that make sense, Niles?
Yeah. Is it? Yeah. Yeah.
So if you just play around with it a little bit now, you can kind of see. And so I was hoping this is something you would do, and hopefully you've already been doing that instead of listening to me. But are you feeling okay on this? I want to show you something here. We now have covered the last part. Whoops. Oh, Niles, did I cut you off or were you good?
Oh, it was good.
Okay, I thought so. Sorry if that.
No, thank you.
Yep, okay. So I know, I just want to show you that big crazy website we used last time. Remember that? And show you where this fits in, LRC Madness. Remember this one? What we were talking about is this part right here. Do you remember that? So just take a second to watch what this means so you can tie this all together, get some understanding. So again, we're looking at, here's the source voltage. V naught is fixed. We're going to sweep the frequency and watch what happens to I max, the amplitude of this wave, right? So as I change the frequency, we get a different amplitude. Notice this plot right here says Z to the -1. Well, isn't that the same as I max? Because I max by definition was equal to V0 divided by Z, which is basically Z to the -1 times a scalar. That's why they're plotting Z to the -1. As I change the frequency, there's some special resonance frequency. And then just like we saw before, if I change the inductance, I could change the location of the resonance peak. If I change the capacitance, I could change the location of it. If I change the resistance, I change the height of it. Got it? So resistance changes the height of the resonance peak. Capacitance and inductance change the location of it, left and right. Feeling good on that? Questions from Zoom or in class, anybody? I'd like to summarize this because this is something I expect you to know cold on test day. All right, so let me get rid of this. And let's go to the board. All right. Oops. All right. Save a copy of this if you have it, because you could use this on your lab Thursday. Okay. So on lab on Thursday, the idea is we're going to have different values of L, R, and C. And hopefully what you can do is punch in some new values and then literally add in a couple extra columns for the experimental data and see if the dots line up close to the theory. You know what I'm saying? So hopefully that's done some of your lab work for you. And then we're on this board. Okay. Summary of what we were supposed to learn, right? Okay, so we had I max and Z versus omega. And this is a series LCR circuit with AC source. And rather than think about that, let's literally draw it. You can put them in any order, but it's probably easiest to do the resistor at the bottom for reasons you'll see on Thursday in lab. So what I mean is the AC source means it's V naught sine omega t. Okay, in both of these, we found that there was a special frequency. Let's label that omega naught. And we know that omega naught is equal to 1 over root LC. Okay. We knew that Z was equal to the square root of R squared plus the quantity XL minus XC squared. We know that XL was omega L and XC was 1 over omega C. As a result of this, if you go to low frequencies, this blows up to infinity. If you go to high frequencies, this blows up to infinity, but it happens a little bit slower. There's one special frequency here. Trying to get it right at the bottom. What was the value of Z at that one special frequency? R. Because if omega equals omega naught, the special frequency, we know XL equals XC and Z equals R from this equation right here. That's what we were just saying. Next, the current. If you have infinite ohms, how much current amplitude do you have? 0. So we start out with no current amplitude. If we go to high frequencies, which term dominates at high frequencies? XC. Again, no current. And there's a maximum of I max right in the middle. And what is the value of that maximum? In general, the value of this curve was V naught over Z. But the special maximum of I max is
V naught over R.
V naught over R. Feeling good on that? What do you think? We found the following information. Increase R. Whoops, that's not. Increase R. What happens to the plot? I max versus omega gets shorter, right? And what happens if we increase L or C? What did that do? What did it do to the I max? And that was true either way. I'm hoping you have this on lock on exam day, because sometimes what I will do is I will literally give you information for a question in the form of a plot to see if you can read the plot. And notice, what are the things you can get out of these plots? In particular, do you agree it's pretty easy to identify the resistance in a circuit by looking at the Z versus omega plot or the I max, right? Or I guess in theory, I could tell you the resistance in this plot and you could figure out V naught, something like that. So it's very common for me to ask one version of the class, say like Z versus omega, another version of the class, Imax versus omega. I might make you sketch these and more on that later today, but yeah. Feeling pretty good on that? There was one other thing I forgot to plot. Do you remember what it was? What was the last piece of information we made a column for that I forgot to plot?
Phase angle?
Phase angle. Let's take a look at it. In the interest of time, maybe I'll show you what we expect. Let's make a prediction before we plot it. This one. So if I was going to plot phi versus omega, I want you to remember ice, right? Eli, the ice cube, I think is what we used in this class. My claim was when I write this down, this is supposed to help you think about phase angles, but maybe you don't remember. Okay, ice. That means cap dominates. You remember that? Capacitor dominates. Does the capacitor dominate at high or low frequencies? Remember, X sub L is 1 over omega C. Is that big when omega is big, or is that big when omega is small?
Small.
Small. So the cap dominates at low frequencies. And what is the phase angle equation? Tan inverse of XL minus XC over R. Would you expect the phase angle to be positive or negative if XC is hella big? Phi should be negative. Is this helping at all? Do you remember this from last time? Okay, so now at low frequencies, the capacitor dominates. Should I get a positive or a negative number? Look at your table. Look at the low frequencies. What's the phase angle in degrees, approximately? Negative 90 degrees. So we're going to plot this in degrees here. So I bet you the other one goes to positive 90 degrees, right? And then G, what value do you think it takes at omega naught? Well, at omega naught, what's true about these two things? They balance. What's the phase angle? 0. So it's going to do something like this. Whoops, that's kind of sloppy. Let's plot it and see. Make the plot. I'll bring it back up. You got your Excel table. If you already made it, cool. If you didn't, my bad. I guess I'll bring this back up real quick. Hopefully it turns on. I'm going to make the plot really quick. You've already got it. I don't know. I know this seems to take a long time, but I truly believe if I'm going to test you on this and expect you to understand it thoroughly, I'd rather cover it at a nice slow pace. I don't know. Hopefully that was a slow pace. Oops. Oh, I grabbed the wrong one. All right. And hopefully in lab, you'll be less frustrated and actually have better success and enjoy the lab a little bit more. Basically, you'll be using this spreadsheet and then layering on the this. There it is. Let me get this for Zoom real quick. There's the plot. So to be clear. All right, so now we've seen all the possible plots that I can make on these. if you're doing your homework and you want to take this, you could save a new copy of the spreadsheet and plot the results for each different question. The numbers in this question are similar to the numbers in problem. I took it for one that's very similar to what we're doing. I'm trying not to waste your time there either. Give me a sec. The numbers are pretty similar to 31.11. All right. All right. Questions? Are people feeling okay on this? Yes, good, yes. How about on Zoom? Are you feeling okay on this?
Yeah, pretty decent.
Okay. You'll really get to know it when you have to take the data on it in class on Thursday, in lab on Thursday. All right. It's coming on the test, coming on the final. All right, and we can go to this board. All right. 5:33. I'd like to cover something new. Okay. I expect you to have this board and that board internalized on test day. Those of you on Zoom, got that? I want to make sure you got that.
Got it.
And you could read all that crap?
Yeah, looks fine. And
Okay.
we got it in the YouTube video.
Yep, you may need to go back to the YouTube to make sure you got it. All right. All right, so I'm gonna erase and get started on something else, and I'll show you some ways I might mix this up on test day. I feel like we've beaten the crap out of this plotting stuff now. Just so I know, in your opinion, was that too slow, too fast, or about right? Just be honest with me, because I might do this again next year. What's that? It was a little fast? Oh, shit. Okay, my bad. Okay, next time, just ask questions. On the Excel part? Because you're not, yeah, okay. Okay, yeah. So, all right, my apologies on that. Hopefully, the YouTube video, you can go back and watch it if something screwed you over, but. Okay, all right. I like having this so that we could actually play with the equation a little bit and see how the plots move prior to lab, because now I feel lab will reinforce it. So hopefully that was the goal here. We'll see what you think come test day on the final exam. All right. Okay. Let's say I did something like this. I'm going to pick a set of numbers. In particular, I want to do a variation on this problem. Oops. And let's say I give you whoops, that's not right. Let's say I give you this information in a word problem for a physics test, okay? If you see all this, how would you figure out the impedance? How would you figure out the inductance? What else could we figure out? Let's start by making sure we understand what was given to us. Remind me what this term means physically. What is it? Source, voltage, amplitude. It is not the voltage as a function of time. It is the amplitude of that function. Okay, C we know, this is the phase angle. Resistance we know. What is omega? Frequency. Okay, by that, is it equal to 1 over the square root of LC? No. This is operating frequency, right? I'm trying to hammer this in, right? All I want to do is have my students pass and get jobs, believe it or not. Now, strictly speaking, because it's omega, I should also add the word angular, right? Now, most textbooks kind of leave that out. They kind of use the units to tell you whether they're talking about angular frequency or frequency. All right. Let's say I want to get L, right? Let's say I want these things, L, Z, I max, and I as a function of time. I bet you're appreciating the workbook right now, right? Because normally I don't make you write all this crap. Any thoughts how we would approach this? Which one of these parts would you want to attack, and how would you attack it? I want those 4 things, L, Z, I, max, and I as a function of time. What's the first piece you might go for? Inductance. I hear inductance. All right. If you wanted to get the inductance, what would you use? Take a second to kind of play around with it, right? I'm trying to simulate a test environment here. What would you use? Obviously, we've got dozens and dozens of equations.
You can get XC.
XC. We can get XC. Do you agree? I like that. So just remind me really quick, how would I get XC?
1 over.
Omega C. Got it. So we're going to know XC. Excellent. Okay, then what?
Use the phase angle.
Phase angle. I like that idea. Let's see if we can get this. Isn't phi equal to tangent inverse of XL minus XC all over resistance? Perhaps it's worth it to draw that phase triangle so you get in the habit of drawing that phase triangle. Just do it, because then on test A, you don't have to think. You're just doing it every single frickin' time. We got our phase triangle there to remind us of the equations. Now let's take a look in here. Phase angle, we've got it. Resistance, we've got it. XL, we've got it. Do you agree we should be able to get XC? And then because we know, oh, whoops, I switched it. My bad. My fault. We know XC, so we should be able to get XL. Nice job. And then what's the equation for X of L? Remind me. Omega L. Since we know omega, we can get L. We're going. This is typical of the thing. You kind of have to like stumble around and be like, okay, I don't know. Once we get that, do you agree the problem is essentially exactly the same as the last one we did? Because how would you get Z at this point? What's the equation for Z? Square root of crap. And now that we know the inductance, the problem goes. How would I get I max? And then how would I get I as a function of time? Do you know that one? I max. Do we have all the pieces? Did we even need the resonance frequency here? No. However, why might it be useful to kind of think about the resonance frequency? Let me ask you this. Once you get all this, what does a positive phase angle tell us? If we have a positive phase angle, I want you to think the following information automatically. Eli or ice? Well, remind me, who's dominating here? If you have a positive phase angle, look at the equation. Which one of these terms is positive? XL. So who's dominating? So if L dominates, what word should I write? Eli or ice? Eli. Okay, so in this case, would you expect a positive or a negative phase angle? I guess positive. Well, oh, shoot, we already got that. So I guess that's what the positive phase angle is telling us. Sorry, I keep getting text or something here. So the positive phase angle tells us that this is dominating. Oh, so what does this tell us about omega relative to omega naught? That's where I wanted to go. If L is dominating, do we have a high frequency or a low frequency? High frequency. So is it bigger than omega naught or less than?
Bigger than.
So that's a way you could check your work. That's what I was trying to bring up out of this. Sorry, I got lost on the phase angle here. Obviously, it's positive because it's positive. Yeah, wow, positive is bigger than zero. But yeah, that's where I was wanting to go with this one. A larger frequency. Inductor dominates a high frequency. What do you think? Good? I hope this is giving you a feeling for how I might try to trip you up on testing, right? I just try to mix it up a little bit. What's another thing I could tell you, right? How about there's two other pieces that commonly show up. Power average, and then sometimes there's a relationship between RMS and Imax. Does anybody remember the relationship between IRMS and Imax? Over √2. So sometimes, just remember that sometimes I'll say RMS in the problem instead of Imax. It's the same crap within a factor of √2. It's a constant. So I'm not trying to mess with you. I'm trying to make sure you know this fact. And keep in mind, this is written on the back somewhere for a voltage, I think. I would like to point out the following here. I'm running out of room. I'm going to squeeze it in here, right? See if that shows up on Zoom. Ah! Okay. All right. Whatever. All right. All right. So the idea is you can use this relationship 1 over √2 for voltage or for current. And that's what I'm trying to point out here. Is everybody cool with that? So even though on the equation sheet, I think I only listed this one, the same thing applies here. So if you forget that number, just remember that. What's the power average equation? Does anybody remember? I would say it's IRMS squared R. Do you see it on your equation sheet? So here's a way I could mix it up with you. What if I give you the average power instead, right? Are we pretty good on this now? Are we happy with these problems? I feel like we spent a couple of days on it. It was really complicated. I feel like you're getting to know it now. I would like to move past this. All right. All right. 5:45. Before we move past it completely, let's do a different type of problem here. 31.5. Look at 31.5 really quick. Let's see if you actually learned something. 31.5. Variation again. And let me do this. 31.5. On this one, Okay, we've sort of seen this problem before. If you look at those graphs, look carefully at the vertical axes. I was plotting IRMS. But if you recall, isn't IRMS equal to I max over root 2? So basically on this axis, I'm plotting the current amplitude versus frequency. I'm just using the factor of root 2. All right. Now in this case, we see one of them goes up like this. We see the other one goes like this. It's 4 times smaller, right? Keep in mind, this value should be VRMS divided by R2. And this value up here should be VRMS divided by R1. Now keep in mind, why am I using VRMS, not V0? Because we're on an RMS plot. Everything gets divided by root 2, right? Okay, now in this case, there's one final attribute which I have not yet discussed. It's called the width of the peak. The width. So it would be nice if we had some way to characterize this width. There are many different ways to describe this. The most common is to use FWHM. That means full width at half max. So the idea is you can look at the plot and say, well, well, it looks like this is the maximum. This is about half. You could call this the width, or the FWHM, full width at half max. Now, I don't care what branch of science and engineering you're in, you will probably see this again somewhere, okay? Civil engineers, mechanical engineers. Now, you might say we could call this width some term like maybe this much right here is delta omega, right? It's a change in omega to get from here to here. It's a delta omega. And we could say that the width here is omega naught plus or minus delta omega, some amount of radians. Everybody okay with that? Now, there's a bunch of work here. You can figure this all out. The main thing that happens here is you can set Z equal to 2R, right? If you have Z is 2, right? Do you agree that at the maximum, Z is equal to R? So to cut it in half, Z would equal 2R. So if you set Z equal to 2R, doesn't that give you a nice, easy equation to solve for omega? You see that? Couldn't you take this ugly equation and solve for omega? That would give you these values right here and right here. You could solve for these special values of omega low and omega high that give you these delta omegas. Now, out of all that, that's fine. That's interesting. There's a thing called a Q factor, right? The Q factor, making sure I don't screw this up, I believe is omega naught over delta omega. And I believe this is written somewhere in that problem. Yeah. All right. So I kind of walked through this, but I think this gives you the basic idea. This Q factor, think about it. If delta omega is small, what happens to Q? Yeah. What does the graph look like? If delta omega is small, is the graph tall and skinny, or is it short and fat? If delta omega is small, if delta omega is small, it's tall and skinny. So what we're going to see here is there's a general class of circuits called high Q, right? This would be a high Q circuit, or small full width at half max. If you have a small FWHM, you have a high Q circuit. The more resistance you add, right? The peak gets broad, okay? This is called a low Q circuit, or it's wide. Short and wide. Now, different types of scenarios, different types of physical situations, you might want to use a high Q or a low Q circuit. I'll give you an example. Radios. Radios, you want a very high Q circuit. You want to tune in on one radio station, not multiple radio stations at once. So you want to have a very narrow delta omega so that you can get exactly the frequency you want and filter out all of the other ones. So in radio circuits, you want to have an inductor and a capacitor and zero resistance. And the only resistance in the circuit would be the resistance of the wires themselves. That's where you get these things where you have like 0.7 ohms and stuff. You may be saying like, I'm never going to have 0.7 ohms of resistance. Well, if you take out all the resistance and all you have is wires, you might get this radio circuit. And I should be clear here. What am I plotting? IRMS or Imax, whatever. It's the same thing, right? And this is omega. Now the low Q circuit, right? The advantage of a low Q circuit is it's not that responsive to any general frequency. Let's say you're building a bridge and a large range of frequencies of earthquakes could occur and you don't want your bridge to collapse. You don't want your bridge to respond well. Maybe you want your bridge to have a low Q. So you would design a physical system such that it has a low Q deliberately so that it won't have violent oscillations and respond violently to an earthquake or something like that. Or perhaps you're building machinery. All right, whatever. So depending on the applications, this type of scenario can come up in mechanics, civil engineering, electrical, etc. And again, all of the math that we're seeing here, yes, it's circuits. Yes, maybe you're like, I'm never going to do circuits. I hate you. Well, that's fine. I don't care. It's probably useful in your major, no matter what it is, if you're stuck in this room right now. So that's why I'm talking about it. I feel like this is enough on this. If you want to learn more, you could do that problem. I will say this. This is another classic way I could try and mess with you on the test. I could give you the value of Z and make you solve for omega, right? If you want to solve for omega, you're going to have to do what process? If you had this equation and I said solve for omega, what are you going to have to do? What's that? Square both sides. Okay, sure. Let's say we have 4r squared equals r squared plus omega L minus 1 over omega C quantity squared. Then what? What type of problem is this? I'm solving for omega. It's a quadratic formula in omega to the fourth, right? So you have omega squared, and then you're going to want to multiply by omega C to get rid of the basement. All right. I'll let you guys do that on your own. All right. Good. Now, I should mention something here. I talked about this whole problem as if current was cut in half. There's a whole variation on these where sometimes they talk about power being cut in half. And to be honest, that's more common. And what happens there is you get a square root of 2 here. Because there's power as I squared R, there's a square root involved. So if you do this again with power, you could get a square root of 2 there. Good on that? All right. I think this is a good time to take a break. Huh. Before we do that, I'll babble a little more. I want to mention something at the bottom of page 203. I'm still on the whiteboard here, somewhere in existence. Okay, there we go. I'm at the bottom of page 203. If you are curious how you wanted to use calculus to get the RMS value, look at that formula at the bottom of page 203. Does everybody see that? If you have a periodic function and you need to get the RMS voltage, that shows you how to do it. If you need to practice that, if you want to understand where that square root of 2 comes from, do problems 31.9 and 31.10. If you wanted to know that that was not on the test, I can tell you right now, that's not on the test. But if you want to know what you're doing, there it is. Got it? So if you're somebody that needs to really know that to be happy with your life, I got you. Now let's take a break. Okay, you need to understand RMS. There it is. Woo, that was intense. Maybe I'll erase the board. Everybody got it? Okay. All right. I'll hit that screen. I was mentioning to Christian out there, I don't really like doing a lot of problems where I just give you some equations and don't explain it that much. This is an exception because I feel like these topics are important and yet they're really difficult to explain. However, I feel like we could get to some conceptual knowledge. Up until now, we've only been doing the series LRC circuit. So now I want to talk about something. And let's look at question 31.12. We're going to go into a topic called filter circuits. This is the last topic that's on test 3. Okay. Okay. Filter circuits. So part A. At low frequency. What's that? Oh, thank you. Wrong board. My bad. Thank you. Part A. Is that better?
Yes.
Thank you. If you're at a low omega, what did I say there? The capacitor has time to get fully charged. Or almost fully. How much current flows when a capacitor is fully charged? No current. Or very little current. Would you agree with that? So if you have low frequencies, we would expect very small current. Okay. What's part B? When omega is much, much, much less than the resonance frequency, that's what I mean by low frequency. What does the capacitor act like? An open switch or a closed switch? Does it act like a short circuit or does it act like a break? So the term we're going to use is break. By that I mean an open switch. No current flows through an open switch. No current flows through a broken switch. Okay. Now what's the next one? High frequencies? Yeah. And high frequencies if you oscillate very rapidly, the capacitor doesn't have time to charge up. I can show you this. Think about this. Tau for an RC transient, right, is something like RC, right? This is approximately the time scale for a capacitor to charge. The period is 2 pi over the driving frequency, omega. If omega gets really big, the period gets really small, and it gets really small compared to the time required to charge this, it's never going to charge up at all. Is it going to act like a break or a short? If it never charges, the cap acts like a short. Sometimes we say closed switch. Is everybody okay with these terms? I'm going to start using break and short all the time now. Okay, so I'm going to say it acts like a break, meaning no current flows, or it acts like a short, maximum current flows. Good? All right. What's part D? Okay, so D. We know the voltage across an inductor is minus L di dt. All right. If we use low omega, much, much, much less than the resonance frequency, things change quickly or slowly. If you have a low frequency, things change Super slowly. Yes. Does the inductor act like a short or a break if you had to guess? Well, if there's almost no change, how much voltage is across the inductor? 0. Inductor acts like a short. No. Short. All right. If you change it very rapidly, what's going to happen to this? If you change it super rapidly, is this going to be a large term or a small term? Huge. It's going to act like a brake. All right. So far, so good. And maybe this is part D through F. I don't know. Somewhere in here is parts E, D, and F. I don't know. Okay. So far, so good. Look at the page. Look at the next page. I've summarized that with pictures. Okay, so 206. You can literally redraw the circuits by replacing the inductor with a straight line. That's what I mean by a short, or the capacitor with a break. So I'm going to catch up while I erase the board. You take a second to look there. There should be 4 of them that are not listed. We can have to fill in just a minute. So we have an inductor, a capacitor, an LC in parallel, and an LC in series. Okay. We've got basically 3 special frequencies we could talk about. High, low, and resonance, right? So and the last one is now, this top one, it doesn't make sense if you don't have both of them, right? If you only have an inductor or only have a capacitor, we can't have resonance, right? So you only have resonance when you have an LC. And let me make sure I'm doing this the right way. Low, high, okay, good. So this is what we said. At low frequencies, this one looks like a short and this one looks like a break. At high frequencies, it switches. This one looks like a break and this one looks like a short. So now, remind me, let's go through here. What happened with the LC in series? Remember when we had an LC in series? If you're at low frequencies, what's going to happen? If you're at low frequencies, you think it's going to act like a short or a break? Low frequencies, what does the capacitor do? It acts like a break. Well, if it's acting like a break and it's in series with this, I don't care if it's a short or not. If you open this switch, do you agree it's going to act like a break? Does that make sense? Yeah. Now, what about at high frequencies though? At high frequencies, is it going to look like a short or a break? A break. Because keep in mind, at low frequencies, the capacitor breaks it. At high frequencies, the inductor breaks it. You see what I'm saying? All right, all right. But what's the special thing that happens at resonance with an LC in resonance? They cancel out and you get a short. Remember that? At resonance, we got maximum current. Remember the current amplitude has that weird peak at resonance? So now, what do you think happens if you put LC in parallel? Let me make sure. Is everybody okay with the top 3 rows before we go on? Any questions on any of that? So now you can use your logic. Think, when you have this circuit, if you're at low frequencies, what's going to happen? What does the capacitor look like at low frequencies? What does the inductor look like? What is the combined effect? A short. Because if one of the paths is a short, they're both, it's a short. So this equals a short. Okay. Well, what about at high frequencies? What's it going to look like? Sounds like they're having a lot of fun with it. Let's see, the inductor is a break, but the capacitor is a short. The net effect is a short. Gee, I wonder what happens here. Take a guess. It's a break. So this one's counterintuitive. I'll explain how if you really want to know in a minute. But for now, I just want to kind of see, you can see that these 2 flip-flop and these 2 flip-flop, agreed? So this is really cool. In theory, what you can do is if you are told a circuit and you can draw it, and then somebody, like say your instructor on your final exam or your midterm 3 says, if this operates at high frequencies, what should happen to the impedance or what should happen to the current amplitude? You could answer. Now I'm going to leave this on this board. You got this on your workbook on page 206. I'm going to walk you through filter circuits conceptually on problem 31.14. Okay, 31.14. So I'm going to leave this up here. I'm going to switch boards in just a second here. I don't know why. I just love this stuff. I find it so interesting. I always have. There's something wrong with it. Okay. Now, I know you know the answer to this problem already. We just did it and spent all day on it, but we're trying to learn how to sketch plausible plots of Z versus omega and Imax versus omega without having to do all the math. All right. So our circuit in this case, is it RLC? Do you agree that's a series RLC circuit? So now what I'm going to do is I'm going to say omega low, omega high. Would this circuit possibly have a resonance frequency? Yes or no? Does it make sense to talk about resonance with this circuit? Do you have an L and a C? Yeah, so it's okay to say. Okay. Well, let's just redraw it really quick. The resistor doesn't change. At low, what does the inductor become? Short or a break? Inductor, low frequency, short. It responds to changes. Low frequency, not changing much. Capacitor, gets charged up, you got a break. If you have a break in the circuit, does it have a little bit of ohms or a lot of ohms? So Z equals infinity. Said another way, what's I max? 0. What's IRMS? 0 over root 2. Everybody cool with that? Just making sure we got that one. All right. Omega high, redraw it. You see where I'm going with this, I hope. What does the inductor look like? Short or a break? At high frequencies. Break, capacitor at high frequencies. Short, what's the value of Z? A little bit or a lot of ohms? A lot of ohms, infinity, right? It's hard to conduct electricity through a big open air gap. or a break in the circuit. So what's I max? The current amplitude is 0. And obviously IRMS would be 0 again. All right, at resonance, what does the circuit look like? You have LC. Are they in series or parallel here? Series. So at resonance, an LC in series goes to a short or a break? Short. What's the impedance? How many ohms do you have? Not 0. A pirate says R. What is I max? V over R. And I would say V naught over Z, which in this special case, nice, Efren, it's V naught over R. Do you agree? Nice. Okay, let's rock. I want to make a plot of Z versus omega and I max versus omega. Okay. What does Z versus omega look like? Show me with your finger. Okay, I'll take it. I don't even know. Do you agree it's going to go here and get to some minimum and then go back up and kind of creep like this? What's the special frequency called on this frequency axis? Omega naught, resonance. What's the special value over here on this axis? R. This is exactly what we discussed at the start of class. What does the plot of I max versus omega look like? Omega naught, it's going to start at 0 and do something like that. What's the special value right here on the vertical axis? V naught over R. Remember, it's not V over R because V is, just reminding you, I just want to clarify, I know, but I'd rather be, boring and have people pass than exciting and have people fail. Okay. Remember, V naught is just the amplitude. When you say V, you mean V of T. When you say I, you mean I of T. So we have to be super anal about how we express these words, just because I'm going to grade you down if you screw it up. So I'm just being straight with you. I'm trying to make sure we practice it every day. Sorry if it's annoying. All right, feeling good on that? We knew this already though. Now, this is just making sure you know the mechanics of filter circuits. Now let's do something cool, something different. Anything other than the same damn circuit we've been doing for days. Look at the next page, 3015, 3115. All right, I'm going to erase the board and get to it over here. You can race ahead if you want. Talk to your neighbor or whatever you want to do. Talk to your neighbor. You might need a megaphone. The room is so sparsely populated. Okay. I'm gonna catch up. We'll do 31.15. On the right board, yes. Okay, and we're doing something that looks like inductor, capacitor, and resistor down low. Okay. So I'm gonna do the same crap. Omega, whoops. Omega less than omega naught, much, much less, all right? What's gonna happen to this circuit at low frequencies? What does the inductor look like? At low, the inductor is a short. Yeah, and remember, it responds to the changes. So if this helps, I think of low frequency as DC, right? Meaning, if you're thinking about low, just imagine if you hooked a battery up to this. That's a really low frequency of 0. So if it helps, you're like, well, a coil of wire, that's just like a resistor. Yeah, and then, okay, so that helps me remember it. And then I just be like, okay, the other way must be flipped. Okay. Omega much, much greater than omega naught. That's going to switch them, right? And then, is there a resonance here? Do I have an inductor and a capacitor in the same circuit? Yes. So it makes sense to do this plot. What happens to this thing at resonance? What does it look like? It's a break, right? It's just totally broken. The idea is if you have this LC oscillator, signals will get trapped in here and oscillate around in there with there. So rather than going through the resistor, it just stops things. All right. So, all right. What's the value of Z in this plot? R. How about in this one? Somebody else. What's the value of Z for this one? R. Yeah. And then what's the value of Z for this one? Total ohms is big or small? Infinity. Nice. Okay. Let's go back. What's I max here? The current amplitude. V naught over Z, which in this case would be V naught over R. Over here. Same. And in the last one, what's the current amplitude in the last one? 0. If you have infinite ohms, you have 0 current amplitude. Let's plot them. Okay. What's the Z plot going to look like? Just stick your arm up there and kind of show me what you think. What's it going to look like? What's that? It's going to be different. Or, well, let's go this way. Do you agree there's our special frequency again? So let's label that omega naught. This way I have it on both plots. Okay. What is the initial value of Z at very low frequencies? No, Z. What is the initial value of Z? R. So I'll put that on here. Do you agree at low frequencies it's R and at high frequencies it's R? And what happens to it at omega naught? Is that what you were thinking, maybe? So it's similar to these other plots over here, but it goes to infinity, right? It doesn't just peak out. And that's the distinction I think I was trying to. Is that okay? So now, what do you think the Imax plot looks like? What's the value of Imax at 0 frequency? If I'm at low frequency, what's the value of Imax? V naught over R. What's the value at high frequencies? At high frequencies, it's the same. What's it in the middle? So draw it with your finger in the air. So, yeah, right? It's going to be something like this. The curve upside down. Now, okay. Zoomers, are you good with that?
Don't you love Zoom?
Yes.
Gotcha. All right. It's so, you're like lulled into it, and then I ask you to respond. You're like, oh crap, I gotta say something. Sorry, my bad. All right, I just wanted to do this. Whoops. I want to look at these two on the same plot. That's why I'm talking to you. All right. In particular, I want to compare these two things. Now, I know you guys have a lot you can do with your life, and for some reason you chose this. This is the cool part for me. All right. Look at this particular plot. Do you agree the resistor in this circuit, or let me say it this way, in this particular circuit, only a very small, narrow band of frequencies will cause the resistor to get significant current? There's a narrow band. It's as if only a small band of frequencies will pass to the resistor. This is a band pass filter. Oh, if you've ever heard that term, that's what it means. Look at this one over here. It's almost as if the resistor gets the same current for everywhere except for right here where there's a notch taken out of it. This is a notch filter. Okay, so depending on the applications, different arrangements might be useful. For example, this one, maybe you want the resistor, maybe you're getting a lot of noise from a radio station nearby when you're doing an experiment. And you wish, man, I wish I wasn't getting 89.7 megahertz all the time. NPR keeps blowing up my circuit and messing up my data. Well, if that's happening to you, what you could do is you could put an LC oscillator in there at 89.7 megahertz, right? 1 over the square root of LC, make it set equal to 89.7 megahertz. Think about radians, hertz, all that crap. If you do that, you can make sure that radio station stops interrupting your data collection. Or more commonly, what's a very common frequency that most stuff in the electronics world works at when you plug it into the wall socket? What hertz is the wall socket? 60? You guys know what I'm talking about? 60 hertz is the general, right? Okay, whatever. Maybe you want to filter out 60 hertz. So you set this up to filter out 60 hertz signals because they're like coming from all the electronics. Anything that's plugged into wall keeps emitting 60 hertz and it's interrupting. Or what if you want to block out everything in your experiment? You're just getting pissed off because you can't get the data right. What could you do to make sure you stop getting stray electromagnetic radiation into your circuit? What's that?
Filter it out.
You could filter it out, but what if you want to filter out all external frequencies? You'd have to do a lot of different LC oscillators. That would be pretty tough. We talked about it this semester. I made Nick stand inside of it. Faraday cage, right? If you put a Faraday cage around it, that's going to block all. So there's different things you can do. If you're getting a lot of noise, put it inside a metal box. All right. All right. Now, what do you think? You want to try another one of these or not? All right. How about we have a little crazy fun? Let's make up a weird problem. There's some examples for you on page 209. To be honest, there's usually one of these either on your final or on the midterm 3, something like this. This is the last new topic. Okay, we're done. So at this point, I'm going to maybe show another one. Niles, Louise, Nick, you all good out there? I'm going to erase.
Yeah.
All right. Thanks,
Yeah, I'm
boss. Thanks. All right. Give me a sec. This is one I thought might be kind of fun. I'll just make it up. How crazy can you get? Let's see. Let's get the right whiteboard. Okay. This is not in the book, so let's just make some crap up. Oh, I don't know. Okay, let's say we had this circuit. Now, hopefully you can tell the difference between my inductors and my resistors. I apologize if I'm not doing a good job there. Can you kind of tell the difference now? Let's assume all of these have the same resistance. And then let's say they have the same inductance too. I don't know, let's look at this resistor here. I'm going to circle. Let's say I want to get a lot of current to that resistor. Okay, is this going to get more current? And maybe I'll call this R1 just so that I can name it up there. You know what I'm saying? So I'll say, does R1 get more current at high frequencies or low? So that's my question. What would you do? Draw it. So let's draw it at high and low. Now notice this one, I didn't ask about resonance. All I'm asking is high or low. So we can do the high and low. We can do this. All right, this is here. What do we get here? At high frequencies, what happens to the capacitor? Short or a break? Okay. And then the inductor is a break. Oh, interesting. This is what happens when you just pull a problem out of your quiver of tricks. Okay. Well, okay. What's the current amplitude in this circuit? What's Z? What's Z look like in this circuit? 2R. Agreed? So what's the I max? V naught over 2R. Everybody okay with that? All right, so what is the low frequency? I have no idea. Let's see. In this one, there's a resistor here. The capacitor acts like a brake, right? What about the inductors? Short. So that means this is a short. What's your gut tell you? I still don't know. Do you know? Do you think it's going to get more or less? What's your gut tell you? It's not obvious, is it? So what do? What's Z total for this one? What's the total resistance? Remember, these are each R. This is R, and this is R. What's the total impedance? How are these two wired? In parallel. So isn't this equivalent to, what's the other resistance when you wire those in parallel? Does it go up or down? What? Yes. More paths. So that means we probably get more current. What's the Z total? 3 halves are, right? 2 halves plus 1 half is 3 halves. So what's I max total? Yeah, it's V naught divided by that, which is 2/3. Is that right? Is that more or less current amplitude? That's more current amplitude, right? It used to be 0.5. This is where decimals help. Do you agree? I'm running out of room. You agree this says I max equals 0.667 V naught over R? Okay, so does R1 get more or less current at high or low frequencies? At low. This is the total. Don't forget, we got to divide it by 2 to split it between the 2 branches. Oh, so fun. Do you agree that here, these two share the same voltage, the current splits? So this means here I would get 1/3, whoops. Right? This would be 1/3 V naught over R and 1/3 V naught over R for the current amplitude in each of these 2 branches. Aren't you looking forward to the final? You'll be done with this class. What do you feel like? Getting it? So this is kind of I just made up the hardest thing I could think of and threw it on the board. And it seems like you guys kind of got it, right? All right. All right. So we've seen a couple of different things with these filter circuits. Let me summarize. Here's an example where you can see, just determine how this thing is going to operate at high frequencies and low frequencies and get a conceptual idea. Another thing was you could plot Z versus omega or I versus omega. Good? All right. Now, I want to show you something else. Go to page 210 and 211. Two words best describe this. Not on the test. It's a very long word. But if you are curious about how these equations are derived, those 2 pages explain how the equations that we've been using over and over that I never explained, that is the explanation. I don't have time to do everything in life, and this is one of the things I got to throw it out. If you're curious, I'm going to bring this up on the main screen since we're done with this, okay? I want to basically bring up the exam equation sheet and talk about a few things that'll help you. And so if you want to pack up, that's good. Let me share screen here. Let me turn this on. Get this down. All right. And so if you are passionate about these problems, that tells you how to do them. Okay. I'm going to go to the exams. Hey, yeah, this is looking good. Let's get these lights. Well, yeah, you can throw the computers back in, and thank you for remembering to do that. At some point, you can do that. You can put the computers away. I want to look now at these kind of the crap that's on the next test. I don't know any shorter way to say it than that. Okay. Biot-Savart law. We've done this, right? You know tricks for straight wires. You know tricks for circular sections. You know how to use the right-hand rule. Grab that wire. Ampere's law. I hope you agree. I told you already, we're basically going to focus, we're not going to deal with the slab. Remember that? I said I'm not going to deal with the slab. But we could have uniform or non-uniform, right? You might have to figure out current density and how it relates or something like that. You might have to make plots. And again, there's usually some questions with right-hand rules. Now remember, when you're looking at these, we usually see stuff that looks like circular cross sections, right? So you have to remember the wires are like going into and out of the page all the time. Remember that? Magnetic flux. Okay, you could have a rod that's moving and you get BLM. Don't get too emotional. Rod on rail stuff. So that's kind of the same idea there. And you know, I spent a lot of time on that, and I told you why. It's because there's good conceptual questions and there's math that relates to a lot of stuff that you do in other branches of science, no matter what your major is. Okay, B field is a function of time near a loop or loop spinning. Remember the women's NBA, omega NBA, all right, or a loop changing size. You could say, basically, you know that EMF is either B perpendicular LV or the EMF was minus n d phi dt. You know what I'm saying? And d phi dt was usually b a cosine theta. You know what I'm saying? We know that. Okay. Any questions on the top part of this? B of art, amperes, or mag flux? And you could ask in office hours or whatever. All right. So now let's go down and look at the last half. Well, we've talked about a couple of different things. RL transients, you remember those? And there was two types of questions. There's basically, actually three types. There was get I as a function of time or voltage as a function of time. Do you remember that? Or sometimes you'd have to solve for R from a plot. Sometimes you had to use a plot. Do you remember those? Where there's a plot and you have to read the values and then you're like, oh yeah, that's right. He said, don't get values close to zero. Don't get values close to the top. I want to pick values somewhere in this sweet spot, somewhere in the middle, right in there. Remember all that crap? Okay. What about LC oscillators? That was our first case where we learned omega naught is 1 over the square root of LC. We talked about the plots. There was only 2 questions in the workbook. And we saw that there's significant differences if you start with the capacitor versus the inductor. And so make sure you do both of those and understand all of that crap. Okay, now damped oscillator. We pretty much didn't get to that. I could explain it to you in office hours. I would love to, but I don't have time. You could read a book. You got to choose your battles. We just don't have time for everything. So we're not doing a damped oscillator in this class. So far, so good with that. All right, finally, I think we beat the crap out of this. Do you agree?
Yeah.
Take a look at that. You know how to do that. You still need to practice it a couple of times. You got some time. Got it? All right. So there's 2 lectures left. One of them's for chapter 32. One of them's for chapter 33. Chapter 32 is super easy. Chapter 33. I guess that says it all, doesn't it? I think it's easy, but it's a lot like this chapter where there's a lot of equations. If you want, take a look where we're going, right? Take a look at page 225. Page 225 is chapter 33. It's dense. It's a lot like this chapter in that there's a lot of equations and we need to kind of understand them. Now, I'm not a huge fan of just saying, here's some equations, memorize how to use them, but I do feel that chapter and this chapter merit that type of discussion at least a little bit. You need to know these types of equations pretty well. So, all right, good enough? Should we call it a night? All right. Just managed to get late and make Nick happy there. All right. Zoomers, any questions? Did that help?
That was helpful.
Yeah. All right. So you're ready to start practicing. All right. I guess I'll end the Zoom then.